Hey, Algebra 2, it is Friday, so let's get going with the lesson here. These are the warm-up problems, so if you have any questions, go ahead and watch this. If not, you can skip ahead on this Edpuzzle, okay? All right, first one, we're graphing a square root function, okay? Remember, square root, only dealing with positive numbers, so this paragraph kind of looks like this going to the right. We are shifting 2 to the left, 1 up, okay? From there, if you make a t-table, you plug in -1, you get 2. If you plug in 2, you should get 3. And again, this graph only goes in one direction because we can't plug in anything less than -2. All right. Domain and range. And also on the test, make sure you draw those nice points, include your t-table. Okay. Domain, there's 2 ways to do it. You can graph it and then look from here, or we can take this square root. We can't have this negative. So if you set this square root, x plus 2 has to be greater than or equal to 0. That means x has to be greater than or equal to 0. So for set notation, we could do values of x such that x has to be greater than or equal to 0 for my domain. And for my range, we can look at this graph as well. We're starting at 1, so we have y values such that y has to be greater than or equal to 1, okay? Yeah, there we go. So again, 2 ways to look at domain. Graph it or take a look at inside that radical and set it greater than or equal to 0. All right, next one here, we're simplifying. All right, simplify for this one. Again, simplify is a broad term. For this one, we can't have a radical in the denominator. So first thing I'm going to do is split apart the top and the bottom, give them each their own radical. So we have the 5th root of 3 over the 5th root of 4. Now, to rationalize this denominator, we're going to multiply by a 5th root over a 5th root. Now, here's the thing. When you multiply these two together, you want to create groups of 5 of everything. So we have a 4. We would need 4 more 4s. But 4 to the 4th is 256. We're dealing with pretty big numbers. So here's what we're going to do. Instead of 4 here, we're going to write 2 squared. Because we already have 2 of something, we want to multiply by the smallest possible thing. All right. You can do it the other way. You're just going to get a big number. So if we have 2 2's, when I multiply these 2 radicals together, I'm looking for 5 total. So I need 3 more 2's, so 2 to the 3rd. Okay. So on top, we have the 5th root. I'm just going to put these inside the same radical. We have 2 to the 3rd, which is 8, times 3, which is 24. And on the bottom here, again, when we multiply these two together, I'm just going to do the long process. We have 2 squared times 2 to the 3rd, which becomes the 5th root of, add those exponents, 2 to the 5th, okay? The 5th root of 2 to the 5th, those just go away, right? Those are inverse operations. Or you can do power over root, and basically you have 2 to the 5 over 5, which is just 2. Okay, so 2 ways to look at it. But if your root is the same as your power, those cancel each other out and you're just left with 2 in the denominator. So there's my answer. Again, simplified for this problem means get rid of the radical in the denominator because math gods don't like that, all right? All right, number 4 here. Again, simplify. So this one, we don't like any radicals in the denominator. So again, I'm going to split it up and give the 4th root of x to the 4th over the 4th root of y to the 8th. Now, you're thinking maybe convert to rational exponent. That only really helps us when we have x's in a couple different spots. We have like bases to combine, but we don't have any bases to combine. Now, from here, I'm trying to look for groups of 4 that I can pull out of each of these terms, okay? Well, guess what? The 4th root of x to the 4th is just x. I can pull out one group. And on the bottom here, I have 8 y's, and I'm looking for groups of 4. I can actually pull out one group for 4 of them and another group for 4, and I've brought out all the 8's, all 8 y's. So I have x over y squared as my answer. Okay, those just happen to be both perfect fourths that I don't have to rationalize that denominator. All right, number 5, here's one where I have x's on top and bottom and y's on top and the bottom, so I'm going to use those properties of exponents. It's already in form with written with exponents, so I just need to play with those properties. All right, parentheses on top, I'm going to distribute this to. Again, I can do this because this is multiplication, so it's not a binomial. We'll get to that in a bit, where it's x plus y. But we're going to have x squared, y squared over x to the negative 1. We're going to flip that, right? Reciprocal is going to move to the top and become x to the positive 1. And then I have that y on the bottom. Okay, from here, my properties say, I'm just going to rewrite it like this. X squared times x to the first times y squared over y to the first. Okay, I am multiplying x's. So when you're multiplying the same base, you keep the base, add the exponents. And then I'm dividing y's here. So that rule says keep the base, subtract the exponents. So I'm just going to end up with x to the third, y to the first is my answer. Okay. All right, number 6, when we say simplify here, this one just means pull out groups of 5 of a kind of anything that I have in here, all right? Now, to remember perfect fifths is a little hard, so here's what I do. I break apart this 96 into prime factors, and I'm going to look for groups of 5 of a kind. So 96 is 6 and 16, which is 3 and 2, which is 2 and 8, and then 8 is 2 times 2 times 2. So let me bring all of these down just to be clear. I have a heck of a lot of 2's, okay? So here we go. And I also need to bring out that negative sign, okay? Because this is an odd root, I can take a fifth root of a negative. So I have 5 2's, okay? So basically, you're rewriting this as 2 to the fifth, and I'm going to bring that negative 2 to the fifth times 3, okay? And then you're looking for groups of 5 of a kind. So I'm going to bring out 1, 2, because the fifth root of 2 to the fifth is just 2, and then with that negative sign, all right? Inside still, I have that 3. It's not a perfect fifth, so it has to stay inside. Now I'm going to take a look at my a's. I'm looking for groups of 5. Well, there's a to the fifth. So I'm going to bring that outside, and I'm just going to bring one of them, because when you've taken it outside of the radical, you've taken the fifth root of it, okay? All right, 9b's, I'm looking for groups of 5. Well, I can take out just one group. And if I do that, I've taken out 5 from the 9. That means I have b to the fourth still inside. Let's take a look at our c's. I have 13. That means I can take out 2 groups, or c times c, c squared. And if I take out 2 groups of 5, I've taken out 10. That means I have 3 left inside. All right, it's nice and colorful. There's my answer. Again, simplify means different things for each problem, but there's how we do all 4 of those, okay? Again, at any time as you're going through today's lesson or the warm-up or homework questions, come back to the Google Meet and I can help you out individually on any problems you want to see, okay? All right, we're going to do a couple things with today's lesson. The first one is rationalizing denominators with binomials. So we have a radical in the denominator, but you might notice, again, binomial is when we have terms added or subtracted. So 1 minus the square root of 5. We can't just multiply by the square root of 5 over the square root of 5, because it wouldn't get rid of the radical in the denominator. You can try it, it's just not going to work. So here's what we're going to do, kind of like when we were dealing with complex numbers and we're going to multiply by the conjugate, okay? So if that word rings a bell, here's what that looks like, okay? The conjugate of 1 minus the square root of 5 is 1 plus the square root of 5. Same thing to the top and the bottom. All right, now we are going to distribute on the top. So we have 6 plus 6 root 5. And on the bottom, we have a binomial times a binomial. We have to FOIL this. So first term's 1. Outside is plus root 5. Inside is minus root 5. So those cancel out. And then the last terms here, we have minus the square root of 5 squared. All right, so on top we have 6 plus 6 root 5. On the bottom we have 1 minus the square root of 5 squared. Those cancel out, right? The square root squared just goes away. We have 1 minus 5. So we have 6 plus 6 root 5 over negative 4. From here, we can simplify this. Remember, we wrote each part kind of separate and reduced each part separate. So we'd have 6 over negative 4, which is negative 3 over 2. And then we'd have 6 over negative 4, which is minus 3 over 2, root 5. Okay, so we can reduce each part as is, or we can leave it all as once, but reduce each fraction. Okay. All right, example 2, same thing here. We're going to multiply by the conjugate. So we have 7 minus the square root of 3 over 7 minus the square root of 3. You might notice here that we have a binomial on top and the bottom, so we have to FOIL twice here. All right, so on top, draw the lines, make it clear. First terms, we have 14. Outside, we have minus 2 root 3. Inside, we have plus 7 root 3. And then the last terms here, we have minus the square root of 3 squared. All right, on the bottom, first term, 7 times 7 is 49. Inside and outside are going to cancel out, that's the point. And then the last terms are minus the square root of 3 squared. All right, let's clean this up a bit. On top, we have 14 minus 2 root 3 plus 7 root 3 is plus 5 root 3. And then minus the square root of 3 squared is just minus 3. On the bottom, we have 49 minus 3, which is 46. And on top, we just have 14 minus 3, so we're going to get 11 plus 5 root 3 over 46. All right, 11 and 46 and 5 and 46 don't reduce, so that's good, and we can leave our answer together like that or separate it. Separating it is easier to reduce it, but this one we can't go any farther. Okay. All right, so when we have rationalizing the denominator with the binomial, remember conjugate, okay? Whoa, where are you going? All right. Okay, next thing we're going to take a look at is combining radicals. This one we're adding radicals, okay? 4 root 3 plus 6 root 3. Here's the thing. Consider the square root of 3 as like a variable, okay? Like if this was x. This would just basically be 4x plus 6x. So you have 4 of something plus 6 of something. This means you have 10 of something, okay? In this case, that something is the square root of 3, okay? So when you're adding 4 root 3 plus 6 root 3, you just add them together, and how many do you have? Now, here's the trick with this. Those have to be the same, okay? Square root of 3 and square root of 3, those have to be the same object that you're adding together, okay? All right, on example 2, we have the square root of 2 plus 4 times the square root of 8. On this one, you can see we're not adding the same thing together, right? Square root of 2 plus the square root of 8. But here's where simplifying radicals come into play, okay? This is why we do it. Think of it this way. Square root of 2, like this is in dollars. And the square root of 8, this is in pesos. You can't add them together. So we want to convert this to the same currency so that we can play with them, okay? So square root of 8 here, if you remember, we can break this down, 4 and 2, 2 and 2. So the square root of 8 is really the square root of 4 times 2, which is just 2 root 2, okay? So we have the square root of 2 plus 4, and then we said the square root of 8 is 2 root 2. So we've brought out a 2, and we're going to multiply it by that 4. We just have the square root of 2 plus 8 root 2. Now we have that same currency, and we can add these together. So we have 1 root 2 plus 8 root 2 is 9 times the square root of 2. So that's basically why we simplify radicals, so that we can do stuff with them if we put them all in the same form. All right, a couple more here of adding and subtracting radicals. This first one, we're looking for the same currency, right? We have 2z to the 5th and 54z squared. So we're going to have to simplify these to see if we can get the same thing inside these radicals. Okay, the first one here, I'm looking for groups of 3 of a kind. I have z to the 5th, so let's pull out some of those, okay? So I have a 12, groups of 3. If I have z to the 5th, I can pull out 1z. And if I do that, I'm left with the cube root of 2 and z squared still inside, okay? All right, this second radical over here, I don't have 3 z's, but maybe in this 54. So let's break down 54, 9 and 6, 3 and 3, 6 is 2 and 3. All right, groups of 3, I can pull out a 3, okay? So I have the z, now I'm gonna multiply that by 3. Inside my radical, any number that wasn't a group of 3, like that 2, gets to stay inside the radical, z squared. All right, now we've converted it to the same currency. We just have 12z times the cube root of 2z squared minus 3z times the cube root of 2z squared. Now we have the same radical. We can play with these. We just have 12z minus 3z is 9z times the cube root of 2z squared. All right, lots of 2's, lots of z's. They all kind of look the same, but that's it. So it looks complicated, but that's the steps. All right, number 4 here. Again, we're adding and subtracting, but we've got Indonesia rupiah, we've got Bali baht, Thailand baht, and where else have I been? I don't know, American dollars, okay? So we need to convert these here. Okay, we're gonna simplify each radical to make these hopefully the same so that we can add and subtract them. Okay, 48 is 4 and 12. So we have 2 and 2, and 2 and 6, and 2 and 3. So there's my group of 4. Okay, again, Miss Avalos showed a different way to do this, but this is how I like to simplify radicals and look for these groups, because basically you've created now 2 to the 4th times 3, and the 4th root of 2 to the 4th, we get to take out that 2. So that's how I kind of look at it. All right, so we had a 5, now we're pulling out a 2, and inside is just that 3 that didn't have a group, so it has to stay inside. All right, minus 3, let's break apart this 81, 9 and 9, so 3, 3, 3, 3, that's a perfect 4th, so we're gonna bring out a 3, and nothing stays inside actually. And then 7 plus 7 times the 4th root of 3, so that one already has the same currency. So we have 10 times the 4th root of 3 minus 9 plus 7 times the 4th root of 3. So the only like terms here are the first and the third one. So let's subtract those, add those. So 10 of something plus 7 of something leaves me with 17, 4th root 3 minus 9. All right, nice work. All right, multiplying radicals, okay? First off, these have to be the same root, okay? The same index or the same root to multiply them. Because remember, we have a property that says if we have like the cube root of a times the cube root of b, this can just become the cube root of a times b inside that same radical if that root is the same. So here's what we're looking to do is multiply these together, all right? So we have the 3 and the 5. We can pretty much write this anyway. So we can write this as 3 times 5 times the cube root of 4 times the cube root of 5. And then just multiply the 3 times 5, which is 15. And we're gonna multiply these two together inside the same radical, 4 times 5, which is 20, okay? So we're just multiplying each part, 3 times 5, and then the radicals together as well. We also want to, when we do this, make sure there's no groups of 3 of a kind in that 20, 4 and 5, 2 and 2, so there's not, so we're good to go on that, okay? Some of these get pretty messy, and we'll take a look at this next one. All right, if we multiply this one, 2 times 7 is 14, 24 times 18 is the cube root of 432. We would have to break apart 432 to see groups of 3, and I'm sure they're in there because that's a big number. So here's what we're going to do instead. First of all, let's simplify first, okay? 24, 8 and 3. 8 is 4 and 2, which is 2, 2, 2, okay? So there's a group of 3 that I can pull out, so I would have 2. There's my group of 3 is a 2, and then inside is that 3 that's not part of a group, okay? All right, times 18 is just 9 and 2, 3, 3, so there's no groups, okay? So 7 times the cube root of 18. But here's what I'm going to do. Instead of writing this as 18, I'm going to write this as 3 times 2 times 2. I apologize, couldn't read my own writing. Okay, 9 is 3 and 3 and 2. So this is actually going to be 3 times 3 times 2. All right, when we multiply these together now, we have 4 times 7 is 28. And now inside the radicals, I'm going to put this all together. The cube root of 3 times 3 times 3 times 2. And you can kind of see that this is easier now to pull out my groups of 3 of a kind. Okay, there's a group of 3 3s. So one of those comes outside. And then inside the radical, I just have a 2. Last thing is 28 times 3. We have 84 times the cube root of 2. All right. If you didn't do this, no big deal. If you didn't break this apart, from this step, you would just get 28 times the cube root of 18 times 3, which is 54. And then we would just have to break apart 54. So sometimes as we get bigger numbers, it's easier to kind of get together groups of 3 like that. All right, I'm switching to PowerPoint because these problems are already done. This is some new stuff for today. We have solving radical equations. So this is 11.3, okay? Feel free to pause these as you go. The animations have the work already done, so I'll explain and point out as we go. Okay, example 1, radical equation. We have x plus 9 to the 5 halves minus 1 equals 31. First thing we're going to do in these problems is, as much as possible, isolate the radicals. So we're going to add 1 to both sides. If we do that, we get x plus 9 to the 5 halves equals 32. From there, what we're going to do is raise each side to the reciprocal of the power, okay? This is to the 5 halves. You're going to raise each side to the 2/5. So that's what that looks like. Now remember, power to a power, you multiply. So really, 5 halves times 2/5 just equals 1. So that's how we get that x plus 9 outside of the radical. All right, the other thing we're going to do is evaluate 32 to the 2/5. So power over root, it's really the 5th root of 32 squared, which is going to be 4. So we're left with x plus 9 equals 4. Pretty simple. Subtract 9, solve for x, we get x equals -5. Now, in these problems, it's very important. Sometimes our answers look good, but they don't work. So it's called an extraneous solution. So for these problems, we have to check in the original equation, we're going to plug back in to make sure it works, okay? So always do that. Sometimes we run into extraneous solutions. All right, this one works, so we're good to go. All right, next one here. This one has 2 radicals. So what we want to do is isolate one of them, basically. Okay, so move one to the other side. So we're going to add that x plus 3 to the 1/2 to both sides. All right, so now we have a radical on each side. Remember, 1/2 power is just the same thing as a square root. Okay, so you can either raise it to the second power or convert to square root and then raise it to the whatever the root is. So this is root 2, so we're going to square each side. Okay, as the square root of something squared goes away, that just unlocks everything that's inside. So we're just left with 2x minus 5 equals x plus 3. Solve for x, 2-step equation, x equals 8. Again, make sure you're checking your answer, plugging back into the original equation. If it doesn't work, it's extraneous. If it does work, if it does not make that, or does make that original equation true, then we're good to go. All right, extraneous. This one has an extraneous solution. Wow, we're just telling you right away, taking all the guesswork out of it. All right. First thing we're going to do, isolate the radical. You see we have a 2 hanging out. Let's move that to the other side, okay? So we get square root of x plus 10 equals x minus 2. At this point, we're going to square each side. Now, here's the key on this right-hand side. We've been doing properties of exponents so much, where it's like x times 2 squared, where we just distribute that squared sign. The only thing is those are factors, right? This is a binomial. So when you square a binomial, you're really doing x minus 2 times x minus 2. And guess what we have to do? We have to FOIL this bad boy, okay? So binomial squared, you cannot distribute that power. Don't do it. I don't want to see it. All right. So we square both sides. The square root of something squared is just x plus 10. We FOIL out this binomial. So we get x squared minus 2x plus 4. All right, how do we solve a quadratic? We're going to set that equal to 0. So move everything to the right-hand side and set it equal to 0. From here, how do we solve it? We factor. So we're going to factor. If you factor, we should get 0 equals, let's see, what multiplies to -6 adds to 5. So it's going to be 6 and 1. So we're looking for x minus 6, x plus 1, and then remember you set each factor equal to 0. So we get x minus 6 equals to 0, x plus 1 equal to 0, and there's our two answers. So the signs flip from factoring, okay? All right, you want to try these into the original equation. All right, I'm going to show you what -1 looks like in here. So back up to the original very first equation. We're going to try x equals -1 just to make sure it's a solution. So we have 2 plus the square root of -1 plus 10 should equal to -1. So 2 plus the square root of 9 should equal -1. 2 plus 3 should equal to -1. 5 equals -1. Something's a little off, right? Not true. What this means is x equals -1 is extraneous solution. Okay? So my only answer is x equals 6. Okay? Our work was good. Sometimes we come up with a solution that just doesn't work in that original equation, so it's not really a solution. All right, here's a good one. Let's take a look. We have radicals isolated, 1 on the left, 2 on the right. So from here, we're going to square both sides. Okay? On the left-hand side, that's nice and easy. Square root of something squared is just x minus 3. On the right here, though, you notice we have the square root of 2 minus the square root of x squared means we have to FOIL this whole thing. So first terms, you get square root of 2 squared is just 2. You get outside is minus the square root of 2x. I'm just combining those. Inside, you get minus the square root of 2x. And then my last terms, you get plus the square root of x squared, which is just plus x. So those inside terms, you have 2 of the same thing. So it's just minus 2 times the square root of 2x plus x. So that's how we get this on the right-hand side of my equation. Okay. Again, we run into, even though we squared both sides, we still run into where we have a radical. We don't love that because we're going to have to kind of do the same process again, which is okay. So let's isolate that radical as much as we can, okay? Which means we subtracted 2 from both sides. We subtracted x from both sides to move everything that we can to the left-hand side. So the x's go away. We're left with -5 equals to -2 times square root of 2x. Now we can square both sides again, and we get 25 on the left-hand side. On the right-hand side, though, this is multiplication, so this is where we can kind of distribute this to each of those things. Right? So we get 25 on the right-hand side. Watch, we get -2 squared, and then we get the square root of 2x squared. -2 squared is just 4. The square root of 2x squared is just 2x, and that's where we get the 8x on the right-hand side. Right, divide by 8, we get x equals 25 over 8. Hooray, except that we need to check it in that original equation, and if you do that, it does not work, so it's extraneous. We want to still show that, and we still want to write that it's extraneous, but there are no solutions for this original equation, no values of x that are ever going to make that left side equal to that right side. All right, we've got a good one here, folks. Heads up, this one gets a little messy, okay? All right, isolated radical already, so we're gonna cube each side, okay? The opposite of taking the cube root is cubing both sides. So cube, cube. All right, so on the left-hand side, that opens up that x minus 5. On the right-hand side, though, you have x plus 1 cubed. Again, we can't distribute that cubed. What this means is x plus 1 times x plus 1 times x plus 1. So we have like a FOIL party here, all right? It says use binomial expansion. It's been a while since we've done that. So what we're going to do is FOIL these first two here. So we get x squared plus 2x plus 1, and then we're going to multiply that again times x plus 1. So take that x times everything first. You would get x cubed plus 2x squared plus x, and now distribute the 1 to everything. So you would get plus x squared plus 2x plus 1. Let's just combine like terms. X to the third plus 3x squared plus 3x plus 1, okay? So that is that expanded form, just a lot of FOILing, okay? All right, at this point, we have a quadratic. We're gonna set it equal to 0, and my work is kind of over everything. When we have 4 terms, remember we do grouping. So we're gonna group those first 2 terms, last 2 terms. All right, we can take out a GCF from those first 2 terms, which is x squared, and you're left with x plus 3. GCF of the last 2 terms is 2, and you're left with x plus 3. Those groups are the same, so you're going to group together the x squared and the 2, and you're going to group together the x plus 3s. Set each factor equal to 0. We get x equals negative 3, and then an imaginary root here because of the x plus 2. X squared plus 2 equals to 0. So no imaginary solutions for these equations. My solution is going to just be x equals negative 3. That's a good one. I like it. All right, we're dealing with a little word problem here. Trunk lengths in elephants given by the equation given here, okay? So L is the length of the trunk, and T is the age of the elephant. If a male elephant has a trunk length of 100 inches, what is his age? So this makes sense, right? In this function, you're going to know the trunk length more than the age of an elephant. Okay? You can't go up to an elephant and say, hey, how old are you? What you can do, if you're studying elephants, you can measure their trunk length, and from there you can find out the age or approximate age of the elephant. So we are given that the length is equal to 100, and we're trying to find time, or the age. So we need to plug in this 100 to the left-hand side of the equation. 100 is equal to 23 times the cube root of his age plus 17. We're going to work backwards to isolate this radical. So I'm going to subtract 17 from both sides. We get 83 is equal to 23 times the cube root of t. Let's divide by 23. So we get the cube root of t is equal to 83 over 23. 3.6. And now here's where it comes into play what we did earlier. Radical isolated, we're going to do the opposite. We're going to raise each side to the third power. So we are left with t equals 3.6 to the third. So 3.6 times 3.6 times 3.6. Or use that little caret button in your calculator or your phone. We get 46.6. Let's see, does it tell us to round? No. So 46.66 years, okay? Don't forget those units. We don't know if that's weeks, months, decades, whatever it is. So 46.6 years, which that elephant looks pretty good for 46. All right, good job today. We have 2 assignments for classwork today. There's a MyHRW and also, I think, a Go Formative assignment. So choose which one you want to work on. Get as much done as you can in class. That way you have less to do over the weekend, all right? Bye.